we have to come up with an equation that will allow our boss to work out when a window cleaner is safe on his or her ladder. So what's the situation here? And we have a window, and we have a ladder. Length unknown, let's call it L, resting at some angle theta to the window. And we've got someone climbing up it. Now what could go wrong here? Two things, I guess. One is that it could be too steep, so the ladder could be really steep, and the person leaning back, in which case it might topple over this way. The other problem, which seems to be the one we have here, is that the ladder could be too shallow, in which case it will collapse here with the bottom sliding out over like that. And that seems to be the issue here. So we want to stop this from happening. Okay, so what's going on here? What forces are going to happen here? This is a statics problem again, because we want the ladder not to move. So what forces have we got? Well, there's a weight from the ladder. There's a weight from the window cleaner. There will be a normal force at the bottom of the ladder. There will be a friction force. And at the top there will be a normal force, and the question says we can ignore the friction force. So let's draw an extended free body diagram and give all those things names. So there's the ladder. So let's have a normal at the base, friction at the base, normal at the top, mg here, and we'll have the force imposed by the person, the window cleaner, we'll call it window cleaner G, and that'll be at some height, let's call it W for the window cleaner, and the whole thing is of length L. So how do we solve this? Well, as usual for statics problems, we balance forces and we balance torques. So let's balance forces. So vertically, upward force, there's only one, which is the normal force at the base. So that must equal G times the two masses, the mass of the ladder, I call that ML, and the mass of the window cleaner. Horizontally, we've got the friction at the base is equal to the normal force at the top. Now we have three unknowns, the two normal forces and the friction at the base, so we're going to need one more equation to solve it, three equations for three unknowns. So let's measure the torques. The ladder is not rotating about any axis, so one can take the torque about any place we like. You'll get the same answers eventually if you work through all the maths, but by a clever choice at the beginning you can make the maths a bit easier. In this case I'm thinking I don't actually care what the normal force at the top is. So if I measure torques around here, the top end of the ladder, then that won't apply. So what are the torques? We have the clockwise torque. The only clockwise torque is coming from this. So the force is NB, and the perpendicular distance is that. So that's theta, so it's opposite for hypotenuse. So torque, so it's going to be NB L sine theta. Clockwise equals the anti-clockwise. So now we've got the friction force here. That's perpendicular distances there. Theta, so that's got a cos theta. So it's F base L cos theta. And then you've got the mass here, which there, plus window G L over 2 sine theta, and the force from the window cleaner, which will be, so it's ML, MW G L minus W sine theta. So here are our three equations and three unknowns. How shall we solve them? Well, the last equation is a bit unpleasant, so let's see if we can simplify it a bit. Notice every term has an L in it, so we can cancel those. W over L, I guess. Now this term over here is the effect of the window cleaner. And you can see that the force at the bottom, which is what's going to cause it to slip, is going to be biggest when that torque here is smallest, which is when L equals W, i.e. when the window cleaner is at the top of the ladder, which kind of makes sense. You'd expect the slipping to be most likely when the window cleaner is at the top. That will make that smaller, which makes this bigger. So let's assume L equals W, because that's the worst case scenario, and then we can get rid of that, which makes it much easier. So let's rearrange this to get the friction force at the base. That's what's going to cause it to slip. So we end up with the friction at the base is equal to NB sine theta plus MLG sine theta over 2. But we already know what NB is. So let's substitute that in. Oh, so it should all be divided by cos theta. So if we substitute that in, we get this, which we can simplify because everything has a G, everything has a sine theta. Sine over cos is tan. You've got an ML here minus half ML there, so it all comes to G tan theta MW plus half ML. So that's the friction force. But how big does it have to be before it slips? Well, if you remember how static friction works, static friction will apply an ever greater force exactly matching the sideways force until it hits the critical value, whereupon it starts to slip. And the critical value is when the friction force over the normal force equals the coefficient of static friction. So what is FB over NB? Well, that's what we've just got up here, G tan theta MW over ML plus MW, G, also times G, so that's equal to ML plus MW over half ml plus mw tan theta. And if that's equal to mu, it's right on the edge. So that will give us the critical angle. So if we rearrange it, we get this. Theta is arctan, coefficient of friction times all these things over here. Now let's check this for plausibility. This equation has just masses on both the top and the bottom. So that has no units, and the coefficient of friction, which is a ratio and therefore has no units. So it's arctan of something with no units equals something with no units. So it's all completely unit and dimension free, so that works just fine. How about plausibility? If the coefficient of friction is larger, the angle can be greater, which makes sense. If the coefficient of friction is 0, i.e. you're trying to put the ladder up with its bottom resting on a sheet of ice, then theta has to be 0. Any lean will cause it to slide away, which also makes sense. If the coefficient of friction is very large, the angle can be large, so that makes sense. But because it's an arctan, to get the angle up to 90, this would have to be, the coefficient of friction would have to be almost infinity. So that also makes sense. You need an incredible amount of friction if you were having an almost horizontal ladder in the situation. How about the dependence on all the masses in this term over here? If the mass of the ladder is much more than the mass of the window cleaner, say the window cleaner has gone on lunch break, then those terms will be 0, and this is just a half. If, on the other hand, the window cleaner, say a very fat window cleaner on a very lightweight ladder, then these terms are negligible and this will be 1. So it looks like what matters is there are two limiting cases. There's 1 when the window cleaner is really the heaviest, and a factor of a half less so when the ladder is most important. And that kind of makes sense, because the window cleaner is assumed to be at the top of the ladder, and so the weight at the top of the ladder is worse than the weight halfway down, which kind of makes sense. So it seems a plausible answer.